Hello everyone, welcome back. Today we're going to be solving Leetcode number 39, combination sum. Given an array of distinct integers, candidates, and a target integer, return a list of all unique combinations of candidates where the chosen numbers sum to target. The combinations can be returned in any order. The same number may be chosen from candidates an unlimited number of times. This is going to be an important kind of part of the solution. Two combinations are considered unique if the frequency of at least one of the chosen numbers is different. Right. So using a little Excalibur draw here to break this down. So we're going to use the test case where we have 2, 3, 6, and 7, and a target number of 7. And like we just mentioned, right, the thing that we're trying to solve is how many unique combinations are equal to 7. Right. If we just look at the array here, we see that we could use two twos and a 3 to get to 7, and we could also use just the number 7 itself alone in the array to get to a target sum of 7. And both of those are unique in the sense that, again, the frequency of at least one of the chosen numbers is different, right? So that's just kind of using our eyes, right? We can see that 2, 2, 3, and 7 are valid combinations, but when you're building a solution, in the sense of coding interviews, right? The first thing you want to think about is the brute force solution, right? So the brute force solution for this problem would be to generate all the unique combinations and then add those that are equal to the target, right? That have a sum equal to target to the return array and return it, right? That'd be a pretty large time complexity, right? It'd be exponential, big O of k to the t divided by m, where k is the length of candidates, t is a target, and m is the smallest candidate. Basically, at every choice, every kind of every choice, you have kind of an option to add another element in the array to your current permutation. And the amount of choices you can choose is t divided by m, because you have to basically take into account if that number that you're going to add is going to take your permutation sum over the target. Right now, the issue with the brute force solution is really two big things here. It's that we're going to be generating duplicate permutations. So basically, we would try 4 twos, and then 3 twos and a 3, and then 3 twos and a 6 and a 7, etc. Right? But then we would also try 3 as the first number, and then 2, and then 3 and 2 twos. Right? But 3 2 2 and 2 2 3, and 3 or 2 3 2, right? They're all the same array, right? They all neither of them are unique, right? Kind of going back to this definition of unique here, right? Where the frequency of at least one of the chosen numbers is different, right? In each of those options, they are not unique, right? But we would generate them because we're generating all of the possible permutations of candidates, right? And also that we really wouldn't be pruning properly. I wouldn't be, again, like pruning these duplicate elements, because, again, we're generating all the possible permutations, right? So the question is, all right, how do we improve this, right? How do we improve the time complexity on this? And the way we do that is using a strategy called backtracking. So the way I like to think about backtracking, it's usually based in recursion. Sometimes it can be done iteratively, but most of the time it's done with recursion. It's a depth first traversal of the decision tree, right? And so what is the decision tree in this case? Like I mentioned up here, right, when we were going over this time complexity, the decision we have to make at each kind of iteration is do we add the current number that we're at, or do we add the next number to it, right? And so that choice that we have is basically which number in this candidates array do we add to our permutation, right? And then we also have to think about a base case, right? When you're thinking about doing tree traversal, especially with recursion in mind, when I think about a base case to know when it's time to eject right out of a path that you're going down, so that you don't just infinitely recur until your computer blows up. So the base case in this scenario for this problem is when the sum of the current permutation is greater than target, right? So when the sum of all the numbers that are in our current permutation is larger than the target, we know that we can stop going down that path, because it's only going to get worse from there. And there are going to be no valid options down inside the the tree of that path down in that subtree. So I kind of did a little illustration here to kind of show what the recursion tree would look like for this. So basically what we would do is we would write a function, right? This function is going to be called recursively, and we just call it backtrack in this case. And every time, and with this function, what we're going to do is we're going to pass in the index of the number that we want to add into our permutation. We're also going to pass the array of the current permutation and the total number, the total, which is the sum of that current permutation. Right, so we would start with 0, an empty array, and 0 as our total, and then we would add 2 to the array. Right, we add 2 to the array. We check our base case. Right, we check to see, okay, is the sum of the current numbers in the permutation greater than or equal to target? Where the answer is no. So we would add that same number again. Right, now it's important. This index tracking is important because that's what actually allows us to stop generating multiple forms of the same permutation. Right, like I talked about with the brute force solution, where we would generate a combination of 2 2s and a 3 multiple times. Right, if we keep track of the index and only add either the current index that we're at or the one in front of it, we stop ourselves from actually making those kind of duplicate permutations, those non-unique permutations. So kind of getting back to our example here, right? So we would add 2 to the array, see that it doesn't satisfy our base case, so we would move down, add another 2, see that doesn't satisfy our base case as well, move down again, right? So we're kind of recursively calling this backtrack function. And we're kind of illustrating this call stack here. So we would add another 2 that still is not greater than or equal to the target. So we would add another 2, and now we hit that case. So where we have 4 2s that's equal to 8, and we're larger than our target. So we would backtrack, right? We would go back up. We would return this function, right? And that would cause us to go back up in the call stack. We would pop that last 2 off of the stack and then try the number that's in front of it, right? And so we would call backtrack again with this, right, with an increased index. And so we would add that index again, see that it is, larger than the target, pop that off, call this again, and kind of continuously do that until we try every possible option. We see that none of these are valid. So, we would go back up to 2 2s, right? Pop this third 2 that we just added off, and then increase the index and add the 3. Well, now that we see 2 2 3, right, that is equal to 7. So that is a valid permutation. So we would add that to our result array. And then, but this is the important thing here. Since we're at the target, we know that we can't add any more numbers. If we try to add any more numbers, it's going to be invalid. So we can basically just eject out of this path and go back up to 2 2, right? And call this again, right, with the next number in the array, which is 6 and 7, and both of those are invalid as well. Right, now, once you would try all these kind of possible options, right, for 2 2, you would actually go back up here and do the same thing that you were doing down here, right, where you pop the most recent number that you put into the permutation off and add the number that's at the index after it. Right, so we would pop this first 2 off and then add 3, right, and then we would basically have a subtree similar to this one, right, similar to this one for 2 2. We would have a subtree similar to that for each one of these options, 3, 6, and 7. I didn't illustrate those because none of them have valid options, but we do the same thing here where we basically recursively look through each option, right, each kind of a decision that we have to add a number that's in candidates until we get to all the ones that are actually valid where they equal up to the target. All right, so that is kind of the explanation there. So let's get into the code. All right, so now we're going to get into the solution, coding this up. So the first thing that we want to do is create our return array result, and then we want to start finding our backtrack function. So this function is going to take an index, the current permutation, and the total of the current permutation, that total sum. The first thing that we want to do is check our base case. So we see if total is equal, if total is equal to target, then we want to append the current permutation, a copy of the current permutation. This is important, especially in the case of if you're using Python. A copy of the current permutation to the result array and then return it. And then we also want to check to see if our index is greater than or equal to the length of candidates. And this is important because, like, once we get to that, part of the decision tree or that call where we have like 2227, right, and then we try to pop that 7 off and then continue down the options and candidates, eventually we're going to get to the end of the array, right? So, there is no option at index 4, and so we want to just eject out in that case. And then we also want to check to see if the total is greater than target. And if that's the case, if either of those are the cases, we just want to return. Then here's where we get into actually getting the recursive calls created. So we want to first add the number that we are currently at, right, at index to the permutation. Candidates at index. Then we want to call backtrack with this same index, this current iteration of the permutation, and the total increased by the number that is at index. And then once we kind of go down that kind of side of the decision tree, we go down that path, we eventually are going to get to one of these base cases. And so now we want to pop that last number that we just appended off of permutation. So we do perm.pop. And then we want to call backtrack again with the index increased by 1, permutation, and the total. Right now we don't add candidates or the index to this current total because we just popped it off, right? It's not there anymore. So we just want to do the total that we started this call of backtrack with. And that's pretty much it for the code for this function. So basically all we need to do is just call backtrack with 0, a empty array, and 0 as well. And then we can return the result array, and this should pass. There we are, right? So submit it. And we can see that this is a pretty good solution, 12 milliseconds. This is probably a little bit slower just due to the language we're using. Most of these are probably that are up here are probably written in like C, C++. But yeah, that's the solution to Leetcode number 39 combination sum. Thanks for watching and have a great day.